Okay, so following up on Amazon transaction processing, so we ended up with concurrency. Talked about that, but now we're going to do a quick couple slides recap because we're kind of in the middle of things. So here we go. All right. So remember, when you're doing transaction, these basic principles of atomicity and isolation still apply, although they work, a little differently. Atomicity for transactions is a little different from atomicity for acid properties. So atomicity means, well, it isn't, it's database design, different things. So, all right, atomicity means that a group of related tasks is either all completed or not completed at all. Basically what that means is if you try to do something in the database and it involves multiple parts of the system, at the end of the transaction, all those pieces have to be pointing in the same direction. Either they all show the transaction finished, or they all show that it didn't. So that's the same atomicity as acid properties. It's different from the basic relational database design atomicity, which is about splitting apart individual fields. Okay, anyway. So for example, credit card gets declined, then obviously your internal system shouldn't show that the goods were sold. Your inventory management system shouldn't update to show that the quantity on hand is reduced. The payment shouldn't be expected to be received. You get the idea. Anyway, and ensuring atomicity, of course, definitely requires linkages across systems in your organization and in most cases with other organizations as well, right? The credit card company and shipping are two obvious ones. Isolation, of course, means the restrictions placed on access to data, and there's two big concerns there. Number one is when updates become visible to other users. So in order to enforce this kind of atomicity process so that people only see the system in a state that follows atomicity, you basically say while a transaction is in progress and changes might be happening on some but not all of the machines involved, let anybody peek in there and look at the state of those machines, right? Because if you did, you could let them see the wrong answer. So isolation and atomicity are pretty close buddies as far as that goes. One way to think about it is just intermediate stages of a transaction are not seen by the end users. Now, in practice, isolation works as a trade-off with concurrency. Remember, you can have one or the other to whatever degree. You can't have both. Concurrency absolutely means the ability of multiple users to access the same data, which by definition contradicts the principle of isolation. So, okay. Now the way things work normally, database records get locked to prevent overlapping operations, right? So if there are some records in a database table somewhere that are involved in a transaction, they'll get locked until the transaction is complete, right? And we talked about that with debt and liability today. The idea is it prevents database conflicts, right? It prevents, in some sense, having parts of the system have concurrent access to those same rows. Locking will prevent that. Easy way to think about that, think about Ticketmaster, right? You go to buy tickets for a concert, you pick your venue, you pick your section, it offers you up a couple tickets, right? You say, okay, I'll take and you have a couple minutes to decide whether you want them or not. Well, while they're shown visible to you, nobody else can come in and buy them out from under you. Effectively, those tickets are locked, right? They're locked until you make the decision one way or the other. Okay, and again, this prevents that kind of conflict where you could have multiple users claiming the same set of, glorious front row tickets and, being super pissed at Ticketmaster afterward. Okay, now of course, after the transaction succeeds or fails, the lock will be removed. If the transaction is done, for example, it succeeds, then any part of that data that's relevant to look at, like suppose you buy something on eBay, right? Then afterwards it would show, oh, this item has been sold. That would be correct, right? But it wouldn't be locked in that sense. If the transaction fails, of course, the system gets restored to its original state, because if the transaction failed, nothing really happened. Anyway, of course, like we talked about, high volume, data intensive situations can lock up the system. If you have a lot of processes accessing the same data and they all have to wait for each other to take turns, acid properties can make your system run really, really, really slow. If you're trying to do it like normal disk stuff, you might be able to get by if you put it all in RAM, but even if you put everything in RAM, if your system is big enough and there's enough overlap and enough connections with outside systems, Because remember, even if your stuff is all in RAM, you still got to do these networked operations with other outside organizations, right, to make sure everything is correct. And that's not going to be in nanoseconds. That's going to be in milliseconds at best. So yeah, if you have any kind of these high volume situations, even if you're putting all your data in RAM, if you're interfacing with outside systems, then yeah, it's going to be super slow. Okay. Now, concurrency and isolation, in a way, they both sound nice, right? Concurrency means the ability to let multiple users access data, yeah, which is dangerous, but it makes your system run faster, right? So the fast aspect of concurrency, that's a nice thing. Isolation, of course, ensures data integrity. That's great, but what happens? Isolation limits scalability, right? You enforce isolation, your system's going to run slower, and it's going to run slower and slower the bigger your system gets. On the other hand, concurrency leads to the possibility that your database contents will be inaccurate, or that people using the database will get incorrect answers. So there is no solution to that, right? It's one or the other. But what you do have is options around what can go wrong. So for example, if you're interested in this stuff, I've linked to an Oracle document that talks about different isolation levels. So, you know, there's a spectrum of choices there, from super high isolation to basically medium isolation to low isolation to no isolation, right? And again, there are options in there, and it's a trade-off. But of course, the best practice, strict isolation for high value transactions, right? Like the Poloniex hack that I covered. Obviously, something like that, you're dealing with big money where people could, you know, make off with $20 million. Yeah, you want to do strict isolation there, even if it slows your system down. But if the potential losses are small or negligible, right, or even zero, like Facebook showing different sets of people who have liked a photo that you've posted, but the photo exists in different data centers, it's not at all important that those are perfectly synchronized down to, you know, the microsecond. That's the sort of thing, yeah, you can catch up to it a little bit later. Okay, so that's the idea. Have isolation when data integrity is super important. Allow concurrency for faster access when the data integrity is not super important. Okay, so that's basically our recap. We've covered all this before, but again, never hurts to mention things again. Any questions on any of that? Like I said, it's old news, but hopefully hearing it, second, third time, you know. All right. Next thing, rollbacks. Okay, so a rollback is basically going back to some previous state of the system. So if a transaction fails, you need to restore the system to its original state, because chances are your databases might have a lot of changes that are kind of penciled in, you know, that, yeah, we want to do these things. Those need to get discarded. Or you might have parts of your database that have made the changes permanent, but not all the pieces of your system have made the changes permanent. Some of them fail. Like, what if at the very last moment, one of your database hardware pieces is just unavailable, right? The server fries, whatever. You need to restore the entire system to its original state. You need to do a rollback. So basic method for how that works, you keep some file, some list of all the transactions that have been started but haven't been finished yet, okay? And along with those, you keep the initial state of any data involved in those transactions. That way, when a failure happens, it's pretty easy to return the system to its last known state. Basically, you unpack all of those transactions in order, right? And if they're all isolated, then you know that everything will be okay, right? If there's concurrent access, then things can get a little weirder. Then it's very important that you do them sequentially and carefully. But again, if they're all isolated, you know that any transaction that's still in progress is going to interact with any other transactions. So yeah, you just fix that. And obviously, maintaining rollback record integrity is vital. If there's some sort of hardware failure, system failure generally, and your rollback records are wrong, well, that's just the game, right? You really can't restore your system to its original state. I mean, maybe you can have people dig through like paper archives or whatever and figure stuff out, but you don't want to do that. This is 2022. Who uses paper? All right. So this brings us to the long promised centerpiece of the lecture, what is known as two-phase commit. So two-phase commit is a transaction model that ensures that if you have two or more linked databases After it's all done, you'll know they have the same data values when the transaction is complete. That is to say, all the arrows will point in the same direction. Either all the involved systems will think the transaction was successful, or they'll all think that it failed. Okay? And either way, I mean, you'd like the transaction to go through, but if it doesn't go through, you want all the databases to reflect that. So, for example, customer makes a bank withdrawal using an ATM. You need to make sure that whatever the customer sees on the ATM interface matches the back-end interface. You also need to know that any replicas of that data are correct, and any secondary transactions involved throughout the database, right? So, for example, anytime somebody pulls out cash, that might trigger an operation to, you know, call a Brinks truck to go out and fill up the ATM the next day. It might trigger some number on the bank's required reserves, you know, things like that. So other things that are required also have to end up pointing in the same direction. So 2 correct outcomes as far as the databases are concerned, right? Number 1, the customer gets the money and all the back-end databases are updated to reflect that the customer got the money. Or the customer, for whatever reason, doesn't get the money and the back-end databases are unchanged, except perhaps so that there was a, you know, an attempt to withdraw money that failed. Okay? All right. So here's a picture. And we're going to walk through the picture. The picture is important. Okay. So let's do, I'm going to make it a little smaller. I got to make this a little, there we go. Screen, thank you. Okay. So this is our picture. This is 2-phase commit. Two-phase commit. 12 seems a little small. I can do that. I can do better than that. 16. All right, that'll do. Okay, now the first thing in 2-phase commit is you have a transaction coordinator, okay? So the transaction coordinator is basically some software agent. So think of, you know, a program that coordinates the transaction process, okay? There's some kind of program in your system that manages this, or sub-program, whatever. Okay, that's your TC, that's your transaction coordinator. Your resource managers controls a set of 1 or more databases involved in the transaction, okay? So the resource manager is basically, again, some kind of software agent, just like the transaction coordinator. It's a little program. It's a software agent that controls a set of 1 or more databases involved in the transaction, right? Because the whole point of 2-phase commit, we have a bunch of different databases, not all of them under, you know, say Amazon's roof. We have a bunch of different databases involved in the transaction. They all need their own resource manager, right? Because of permission levels and such. Amazon can't go in and update the credit cards databases. Credit card company can't go into Amazon, update Amazon's databases, right? So they need their own separate resource managers. Now, the first thing that happens, request to prepare, right? So TC tells RMs to make their databases, to verify that their databases are ready to execute the transaction. Okay, that's what transaction coordinator says. There's this transaction we're going to do. Make sure that all your hardware, your software, everything's ready to go for this. Okay, so resource manager tell their databases, right, to, if you like, pencil in the changes, right? They're not permanent, and I obviously do not mean pencil in the changes literally for database software, but you know, the different database machines need to know that this is what we're going to do. We're going to like pencil in the changes for now and verify that they are ready. Okay, so once all the databases have, you know, basically what there's going to be is there's some sort of process queue on each database. So the database is going to see you know, are there locks on these records? Is the transaction seem valid? Does it violate any of the, you know, rules of our database? And can we do it? Is all the hardware up and running? Okay, so that's the sort of stuff that happens. When all databases, I'll do DB for databases, when all databases have confirmed, the RM tells the TC. Okay? So, once each resource manager hears back from all the database it supervises, and all those databases have said, yep, thumbs up, ready to go, then the resource manager can write back to the transaction coordinator, say, yep, all our guys are ready to go. Okay? At the end, over here, when all RMs have responded affirmatively, that means they can do it, right? That means yes. When all resource managers have responded affirmatively, the transaction coordinator knows the transaction is good to proceed, right? If any RMs respond negatively or fail to respond, then the transaction will be aborted, right? They say, nope, it'll time out, right? If the transaction coordinator waits long enough so that the timeout happens, then it just times out, right? Suppose there's actually a broken network connection, like a router fails somewhere in the system, right? Obviously, the transaction coordinator is not going to hear back from the resource manager. So there's a timeout mechanism built in. Or if one of the resource managers says, yeah, sorry, I'd love to do that transaction right now, but for whatever reason, we can't do it, right? If they get some negative response, then the transaction coordinator knows there's no way they can make this transaction point the same for everyone, point positively, so they fall back on saying, we're going to show that the transaction didn't happen, then they're done. Okay? Then, but if everybody responds back, the TC tells all the RMs to make the database changes permanent. Okay, because the transaction coordinator has heard back and everybody's ready to go. So the transaction coordinator says, yep, go, let's do it. Okay, so again, RMs tell their databases to make the changes permanent and, you know, confirm when done. Okay, at this point, right, when all databases have confirmed, the RM tells the TC, right? The RM, all our guys are done, changes permanent, da 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 da. So once again, when all resource managers have responded affirmatively, the TC knows the transaction is complete. Okay? Again, if any RMs respond negatively or fail to respond, then the transaction will be, you know, undone via rollback records. Okay, so there is a slight difference, right? At the end of the prepare phase, if any of the resource managers fail, well, the transaction hasn't been made permanent on any of these databases yet, right? The transaction elements are waiting in the queues to get processed. So, but at this point, in the commit phase, some of the resource managers might have actually had their databases make the changes permanent, right? So at that point, you got to use the rollback records. I should add here one thing I often forget, but I'll add it here, and create rollback records. Okay, so that should happen as part of the prepare phase, you know, that the rollback records get created to, you know, record the initial state of the system. Anyway, at the end, I'll add this here. After transaction, typing is hard on this keyboard. After transaction is done, rollback records will eventually be discarded. Okay, because if the transaction is done, you don't need to hang on to those things forever, right? That would be like hanging on to your tax paperwork for like 40 years. You're just not going to need it that long. Okay? All right, so this is two-phase commit. And remember, the key point about two-phase commit ensures that all involved databases will either show yes to transaction or show no to transaction, right? It's going to be one or the other. It's not going to be both. You're not going to have some databases saying that it happened, some databases saying that it didn't. That would be a horrible thing. Okay, questions on this? Does this make sense? I hope it does. This is two-phase commit. And again, yes, it is widely used. This is a fairly standard basic model. I mean, obviously you could add on any number of details to it. This is the way two-phase commit works. Okay. Now, here's some stuff if I proceed. All right, so number one, right, you can look at this. If I want to look at, oh, you can't see screen. Implementing two-phase commit. Bunch of stuff here. Look how much time I saved you. Okay, and more stuff on the next slide. This is basically the text update of what I said. Same thing here. Again, this is shorter, but still a lot of it talks about it in more detail, but you get the idea. Okay, this is IDS 200, not, you know, IDS 496 for transaction processing. So, yeah. Okay. No questions on two-phase commit? I explained it so well that everybody feels great? Okay. Oh, do I have sound on? Let me see. I guess I do. All right, let's see how things are going with the remote people. What's happening, remote people? Who's here? Oh, look at all of you. Okay. All right. So yeah, okay, that's two-phase commit. Anyway, a couple slides. So we got some other topics to cover. We're gonna, a couple slides about transaction security, a few slides about network architecture, and a few slides about object modeling. So obviously transaction security is important. You don't want people, you know, you don't want bad guys having access to that information, right? So the obvious one is credit card numbers. If somebody steals a credit card number during a transaction, they could do bad stuff with that. But there's other things. For example, just the fact of certain items being delivered and their delivery time, right? There's been a wave of people lifting packages off of people's front steps. You know, you especially hear about that in New York, but it happens everywhere to some extent. And, you know, if the bad guys could look through and see, oh, let's find out when all the jewelry is getting shipped. Let's find out when all the electronics is getting shipped, right? And get a good time for when that's going to get delivered. Yeah, you know, they could really streamline their thieving operations. So you don't want that to happen. And likewise, delivery address, you know, same kind of thing. You can find out exactly where stuff is being delivered. And anything the customer would rather remain private, right? If you're buying some stuff that you perhaps for whatever reason do not want to get out into the public domain, yeah, of course. Okay, so anyway, system security is needed to avoid all those, you know, consequent negative outcomes. So lost goods, lost customer loyalty, any sort of legal actions, right? So if there's, in many cases, if there's a security failure, but the business has put up reasonable defenses against security, you know, the court doesn't find them negligent, you're probably not going to squeeze any money out of that rock. But, you know, if you can prove that the company, you know, failed and had a pattern of failures, then yeah, there's something along those lines. So for example, Target 2013, you know, the court, there were lawsuits and the courts looked at basically the state of the woefully inadequate and half-assed state of Target's security procedures. And they said, yeah, you know, you're on the hook for some of this cost. You got to eat that. But a lot of times, you know, if there's a hack, yeah, stuff happens, you know. So anyway, but it's a risk. So the core detection of fraud, the way that happens is doing some kind of baseline event, comparing each event to baseline historical data. So if you think about it, it's a lot like a spam folder for your email. So how do you think spam filters work? How do you think they recognize particular email as spam? What do you think? Anybody ever thought about how spam works? How do email boxes decide, hey, this email is spam, this isn't? Yeah. Maybe. Maybe. It's possible. Yeah. Yeah, that's a big one, right? It's less about the email. Part about the email itself, but a lot of email from the same source that you're not opening. So there's definitely an end user component to that, right? If you're not looking at it, it's spam. Okay, what else? Anything else?
Let's say there's like bargains at gmail.com, and you can see bargains qrx.gmail.com.
Yeah, maybe something that just looks suspicious in some way. Yeah, I mean, that strictly speaking is not exactly the same as spam, but it gets probably put in your spam folder, so I'll give you that. Yeah. Okay, I would add on the last one. If the source is sending out a whole lot of email to a lot of people, right? Because the email service knows this. The email service knows that not only are you not opening 99% of the emails, but maybe 99% of the users who get email from that place are not opening 99%, in which case, right, that's like a double red flag for spam. That's a spam, it's a flag for the source and for the user. So yeah, the threshold is lower. So yeah, stuff like that, right? So there's a combination of attributes of the sender and a combination of user behaviors that let the system know this is spam. I mean, and of course you can always flag something as spam, which is, going to give the system some information too. All right. So anyway, yeah, it's a similar thing for protection models. Basically, they look at a reasonable baseline of user behavior, and then based on that, they say, yeah, does this transaction look good or not, right? So, for example, normal versus abnormal behavior for a particular customer. Well, when I bought my wife's, I shouldn't say first because I only did it once. When I bought my wife's engagement ring back, way back when, you can imagine I was not the kind of guy that spent a lot of money on jewelry, So I buy this expensive ring and it flags something in their system, and they freeze my credit card, right? And I got to call up the bank and say, no, this is legit. I'm buying an engagement ring. And they say, oh, good luck with that. So yeah. Anyway, right? So that was a flag. The fact that I'm buying, this expensive item. So, and that was abnormal behavior for me. But does anyone know who Mr. T is? Nobody knows who Mr. T is anymore? Who's Mr. T? Yes. He may have rapped. I believe he did have a small celebrity, but that wasn't his main claim to fame. His main claim to fame was that he was on an 80s show called The A-Team, and he was also in the movie Rocky III. He had his little window in the 80s of fame. And then within the last 20 years, after that, he did some pro wrestling stuff. And then after that, he had a little window about 10, 20 years ago where he was doing ads for World of Warcraft. You guys have heard of World of Warcraft, yeah? Yeah, he was doing commercials for them. He's, yeah, anyway, I will find Mr. T. So if you see Mr. T, his defining attribute is that he wears about 5,000 pounds of actual gold jewelry at any given time. So what I'm saying, if Mr. T goes to a jewelry store and buys like $100,000 worth of jewelry, that's not going to be an unusual purchase for him, right? But for me, it was a very unusual purchase to buy jewelry. He's the guy I think of when I think of that much. That gold. All right. Okay. Yeah. So anyway, purchase type, volume, price, all those sort of things. A transaction might look normal for you, but not for someone else, or vice versa. Okay. Other thing, obviously, delivery address. If you're getting something sent that's a little weird for you, there's a little bit more leeway built in if at least it's getting shipped to your usual address, right? But imagine if, it's a very expensive bundle of jewelry and electronics and stuff, and instead of your usual address, it's being sent to a completely novel address in some other country, right? Yeah, it's going to be a huge red flag, right? They're not going to fall for that. Other things, there are certain items that are typical or atypical of fraud. So the things that are easy to fence, you know, to sell as stolen goods are things that are small and expensive and fairly anonymous, right? Jewelry is a great one. Electronics is a great one. Books and toys, not so much, right? I mean, you could conceivably make a $10,000 fake order of books and get that truckload of books and try to unload them somewhere. But realistically, it's going to take a long time to unload $10,000 worth of books. It's not really worth the hassle for any self-respecting criminal, right? Same thing for kids' toys, right? You could buy like $10,000 worth of little crocodile xylophone, you know, 5-note xylophones, but good luck selling that and getting any actual money out of it, right? So again, if there's something in the system where, you know, you do buy $10,000 worth of crocodile xylophones, it would probably get flagged, not as far as theft, but just as far as maybe a mistake, or maybe somebody's trying to troll your account. You know, somebody's just trying to ruin your day by having this ridiculous shipment sent to your house. Yeah. And of course, unusual delivery volume, right? So again, you buy a box of diapers, couple boxes of diapers, no big deal, right? You buy 1,000 boxes of diapers, maybe that throws some big red flag where they're like, yep, nope, this ain't right. Okay, so anyway, just simple idea with fraud detection. This is the same kind of thing. You know, when we were talking about Facebook profiles, kind of the same thing. When we talk about email spam filters, kind of the same thing. The big picture is the system has some baseline idea of normal behavior, and if there's anything that's too far away from normal, that's going to throw some red flags. Okay. Next up, network architecture models. So let's talk about how users send and receive data, right? Because that's how this transaction processing stuff works, right? You have a bunch of users connecting the system to do what they got to do. So what we know is, first of all, the user has some interface, right? The user has some way to get into the system, right? Like you go to Amazon.com and to some extent you're in the system. The business, of course, holds all the data, because if you had the data, you wouldn't need to go to the business, right? So the business has the data. Other details are potentially flexible. You know, the application could be mostly running on a server behind the business, you know, boundary. It could mostly be running on your machine, and the business just receives the results of it. So those other details are flexible. But we'll talk about two major architectural styles. The first one is client server. Second one is end tier. All right. So I'm going to do the diagram first. So client server, you have a server machine that is for exclusive use for a bunch of different client machines. So basically, that means the server machine has to have all the applications and all the data that those clients might need. Now, where this makes sense, imagine if and you know, I guess conceivably the server could be connected to a single piece of storage for data as well. Where this makes sense is if you're on a purely internal work system, you know, where some admin person loads the data onto the server somehow, does those kind of updates, and then the client machines are working with that data. Yeah, you know what, that could make sense, right? There's some kind of standalone project, and at the end of the day, it delivers some deliverable, and none of those client machines need access to multiple databases or applications not on the server or to the broader intranet. That kind of system can work. And in fact, it makes sense that that was the dominant model in the 80s and through a big chunk of the 90s. Reason was businesses didn't really have internet in the 80s, right? I mean, yeah, email existed, but it was unusual. Mostly, again, anything the business needed was kept on a server, like for some department or for some dedicated work team, and then the machines using it would just access that machine to get whatever they needed, okay? So Amazon, of course, needs a network architecture defining how clients send and receive data. So client server, basic model, clients directly obtain data residing on servers, the application logic, the actual application program that runs. It might be a thick one that runs mostly on the client machine. It might be a thin one that runs mostly on the server, but obviously it's got to be on one or the other. Now, the basic problems with the client server model, number one, security tends to be a little bit more difficult to enforce. Why? Because all the end users have direct access to the data, right? Or potentially they can tamper with the client application logic somehow. Because why? Because they're just connected to that one machine, right? Now, of course, to an extent, you can fix that by saying, we're only going to let, this certain select pool of users access this. And, that's how it would usually be implemented. But so that's one issue. But the bigger issue that led to it being abandoned is that it's really hard to scale or modify, right? Imagine if you're basically forced to use one machine. Imagine if you want to run a whole bunch of different applications simultaneously for a bunch of different clients. Not really feasible. Why? Because the applications, they take space up on the machine, they take space in active memory to run well. You get too many clients trying to do too many different applications, server's going to get overloaded and quit, right? It's the same thing as if you have too many active applications on your laptop, they're going to start running slow because they're going to be competing for memory. The other thing, imagine if data gets so big that you can't even store it on a single machine, right? So suppose Amazon tries to do this client server model for its customer shopping. Well, Amazon has untold hundreds of millions of products. The number fluctuates between like 500 and 3 billion, depending on how ruthlessly they prune their inventory and their selection. But at the very least, hundreds of millions of different items worldwide. And there's no way you're going to keep all the information for that and all the historical stuff for analytics and everything else that they need. You're not going to put that on one machine. Just not going to work that way. So, yeah, they got to do something else. Anyway, more about client server. So again, if you're doing small scale private usage, it might be okay. It might be even better than one of these more flexible systems. Why? Because it's cheap and fast to build and deploy, right? You can just buy a server, buy some cables, your clients show up and use it. The data is all stored in one point, so you don't have to worry about replication issues and keeping track of that. There's only one point for patches and upgrades, right? If something has to be upgraded on the server, boom, it's done in one place, and when it's done, it's done. And even though it has some security risks, monitoring security is easier because, right, there's a fairly simple set of connections and access points that you got to manage. But of course, the limitations, expansion and modification are difficult. You can't really break up this server into multiple servers without also reassigning clients to those other servers. So they're not going to work too well. Of course, if you have a thin client model, then as you get more users, your servers are going to get overloaded. If you have a thick client model, then one of the issues that can happen with that is any patching of the applications has to be done on the client side. You have to depend on the users to do that in a proper and timely manner. Even though there's only a single point for patches and upgrades, there's also a single point of failure, right? If that one server fails for any reason, well, that's the end, right? All those guys, they got nothing. And again, users connect directly to the machine holding the data, which means you really need to keep that internal, away from the internet where there's all sorts of nasty security threats. Okay, so client server, again, it had its day. It made sense once upon a time when data was small, manageable, and there was no internet. Yeah. I mean, if you think about it, it really evolved from the first standalone computers, like in the 50s and 60s. Let's say the 50s, right? You designed one massive machine with switches to basically run one program, and then you do some punch cards to put in the data, and then it would somehow signal to you what the output was, whether with lights or printout or whatever. It would tell you what the output was, and that was like single machine, right? There was like one machine, one interface, one user. Client server was basically saying, yeah, same thing. There's one big machine, but now multiple users can use it. But eventually, the problems with data and the number of applications became so big that you couldn't feasibly keep it on one machine, which led to N-tier architecture. Okay, solution to client server those problems is adding intermediate layers, or what are called tiers. So I got a thing here. Let's blow up this. Yep. Okay. So with N-tier architecture, you have some clients, they're doing whatever they're doing. Oh, screen. You have some clients, they're doing whatever they're doing with the interface, right? And here that just shows one client, but recognize that there could be many, many clients in this tier. A tier is a group of machines all doing the same kind of thing, right? Then you have a bunch of different application servers, that are basically running applications. Users are sending them requests, servers are sending back the responses. The application servers connect to a whole big set of database machines, right? We've talked about this with Facebook, that there's no way Facebook could store all of its data on one machine. They need like thousands of machines every day being added to their system to to keep up with the data input. So database tier is this massive, massive set of many, many machines, right? And then I guess in the abstract, they have some database here, but this is all part of the same thing. So these database servers, they're the machines that are like sending out the data, but the database is the actual like disks that it's stored on, right? So you can think of these last two as basically just being storage, right? Okay. So yeah, solution to problems with client server is adding intermediate layers. So rather than just having one server that does everything for all of its connected guys, you have one group of machines running applications and another group of machines acting for databases. So the standard architecture is 3 tiers. Each tier performs a specific set of functions. It's designed in a modular way, which just means machines don't need to know what hardware is being used, right? So for example, if a server is going to send a request to a database machine, it doesn't need to know the specific kind of database machine that it's interacting with, right? It doesn't need to know if it's, a Windows machine running Oracle software, or a Linux machine running some other database application. All it is, it's going to format some database instruction in SQL, and it's going to send it out, and it'll know that the interface will allow translation of that SQL command to whatever the database needs. Okay, so that's what I mean by modular design there. And tiers can be added or can be subdivided, so it is possible to have n more than 3. So one thing, for example, that you might do is deploy modules of applications. So rather than provide, say, a complete copy of MS Office multiple times to every machine, you might say, well, we're going to have 100 copies of MS Word and 500 copies of Excel and 50 copies of Access, stuff like that. And that there could be another tier that controls which application modules are pulled and deployed at any given time on which machines. All right. Anyway, typical way the N-tier model is implemented, it's for thin clients with the application logic on the intermediate tier. So the users reside at what's called the client or the presentation or the user tier. And these different terms, they don't have great meaning to them. They're just different vendors call them different things. So if you buy it from Microsoft versus you buy it from AWS versus from IBM, they can call it some sort of, they can put a different label on it. But at the end of the day, it is the tier of end user machines, right? In the middle, you have the application tier or the server tier, sometimes called the application logic tier. That's where, your applications run. And then databases, right? Often called the data or the database tier. Okay, so typically the clients connect to a server, the server can connect to any one of those database machines, and that effectively allows the client to contact any database machine at all, right? Very different from client server, where the data all had to be stored on a particular single machine. Okay. Anyway, yeah, all right. I'll talk about tight and loose couple. You know what? I want to go ahead to N-tier architecture. I'm just going to keep it going while people are still engaged. So advantages of N-tier architecture. Number one, it's easier to maintain, right? System components are modular, meaning if you want to replace one server with another piece of hardware, it's pretty easy to do, right? All you got to do is make sure that that server conforms to the interface requirements, and then it doesn't really matter what hardware you're using. I mean, yeah, it's nice if it's faster, but the point is the system can work. It's not tied to a particular brand or model of hardware. And isolation. Nice thing about isolation, changes to one part of the system don't directly affect others. So, for example, suppose your number of data machines increases by 1,000 every day. Well, you can expand that database tier without necessarily having to add any new server machines, right? Yeah, you'll have to allow for more connections in some sense, right? You'll have to allow that capability, but you don't specifically have to add on new server machines. Whereas, the client server model, if data starts getting bigger, then, and that's occupying most of the space on the machine, you can't run as many applications. Well, you have to break that up somehow, right? You have to basically say, well, this server can only handle half as many users as it used to. Or if you're saying that the number of applications are becoming more demanding in terms of memory, then yeah, same thing, right? You have to split up that server to work with a smaller pool of end users. Okay, security and reliability. The application logic is going to remain internal to the business, right? Whatever the business boundary is, the business owns those servers, so it's pretty much going to keep that application on its own side. It's going to be really hard for anybody on the outside to go in and breach it and look at how the application actually runs. Data gets accessed through standard interfaces, meaning it's harder to do some sort of malformed, malicious database operation that tries to do something it shouldn't, right? Because it has to pass through multiple stages of the system. It has to be a database operation that not only, can be processed by the database machines, but also makes it through the application servers as well. And finally, easier system testing. Why? Well, client server, you can always say, we know how many users it can support, we know how much data we can store. But the thing is, the application requirements vary a fair amount from day to day, all right? Different users at different times, they might look and say, yeah, you know what, I'm working with small files today, but I'm working with big files tomorrow. And the applications themselves, they get updated over time and may need to use more memory. They may have a bigger memory footprint. And data continuously grows. With N-tier architecture, you always know that if something needs to expand, you can expand that separately, right? If you need to run more copies of applications, you can add on more machines onto the application tier to handle that, right? If you need to store more data, you can add on more machines in the database tier to handle that. So, the testing requirements are actually a lot simpler because there's flexibility and expandability built into the system that isn't really there for client server. And yeah, finally, scalability. So all these tiers can be scaled independently. So if you have a lot of data, but basically the same needs for applications, you can just add on database machines without shelling out cash to pay for more application servers. Or if you're running a wider range of applications or a set of applications that require more memory for whatever reason, but your amount of data is pretty much the same, you can leave your database tier pretty constant and just add on a few machines into the application tier, right? So you can add capacity exactly where you need it instead of having to add it throughout the system like you might for client server. And finally, modularity makes it easier to migrate to cloud. So if you are having this whole set of operations under your own roof, but you're looking at going to, shifting it to the cloud at some point down the road, the fact that it's already broken up into modular pieces will make that process a lot easier. Okay, we'll talk about that more to the cloud system in a little bit. All right, because that's our third lecture. But just, I guess for now, push the I believe button that N-tier architecture implemented correctly, implemented in a really modular way, is a lot easier to migrate to cloud. Okay, so a couple slides about tight versus loose coupling. Okay, so coupling basically means the degree to which system components have dependencies built in. So if you have a tightly coupled system, that means there's a lot of dependencies built in, and it allows the potential for higher performance. For example, if your application knows that it's going to run on a particular machine, it can be designed to run on that particular machine and thus run better. If you have a loosely coupled system, then the components are relatively independent, which has the advantage that it's easier to modify, right? When I talk about modular components and that, say, the database machines only need to be able to understand a query that comes in, they don't need to know the hardware of the server that's sending it, that's a loosely coupled system. So there are some benefits to each. I'll give you an example, non-technical one. Suppose I want to tell you about a movie, right? If this is like a tightly coupled approach to description, maybe I could assume that you and I both speak the same language and we both know a lot of film jargon, so I can provide a lot of detail about the good and bad aspects of the movie, right? My message to you can be fairly detailed and precise, and you'll get it. In a loosely coupled system, you'd communicate through some kind of universal standardized mechanisms, right? So you might have like a list of attributes of the movie, like how was the acting, how were the special effects, how were the scenery, how was the sound, how was the music for it, stuff like that, right? And I could give any of those like 1 to 5 stars, And so you'd get an idea of what's going on, but you wouldn't get the full depth of the message, right? And similar kind of thing with video games in particular. So you know how when you go to the video game store, one shelf for PC games and another for like PlayStation, another for Xbox, another, right? Nintendo Switch, whatever. Why are all those different? Why do you need different copies of software for different hardware? Remember what I said, higher performance? Don't people like to see, you know, pretty pictures in their video games and super realistic explosions and blood splatter and whatever else, right? Yeah, you're not going to get that if you do like a one size fits all. If you write some game in Java and you use like the lowest common denominator of available graphics. So yeah, you write these games in a programming language that's for a specific hardware style, right? So a PC game is written for a specific hardware configuration, right? It's not complete because there could be different graphic cards and what, but it's fairly complete. If you write a game for Nintendo Switch, it's going to run specifically for the hardware that Nintendo Switch has, and so on, right? So that's relatively tightly coupled as far as that goes. Likewise, operating systems, right? Operating systems written for a specific hardware configuration. They're not going to work. It's not going to work if you try to run Mac OS on a PC. All right. So, in tightly coupled system, components are designed and integrated with mutual knowledge of each other, right? The hardware is there. You know what the hardware is. You can write the software to take advantage of whatever quirks and, you know, whatever shortcomings the hardware has. Communication protocols can be designed, you know, again, with specific knowledge of the software that's being run and the hardware that's being used. And again, allows relatively efficient communication. But if any of those above things change, you have to update the whole system, right? If you've written your application to run on a particular kind of hardware, when that hardware becomes obsolete, you got to rewrite a bunch of code because you're going to run it on other machines. But again, in a loosely coupled system, communication happens through standard interfaces. All you got to do is specify the formats of the inputs and outputs. For as far as the hardware and software, there's a lot of flexibility as long as it conforms to the interface requirements. And basically, this makes your system a lot easier to change and modify, including expansion, right? Yeah, you'll take a performance hit, but the machines are so fast these days that, you know, in most cases, taking a 10% performance hit or so is nowhere near as important as the ability to allow for hardware changes, software changes, and continuous growth. Okay, so most systems these days are designed as loosely coupled systems because flexibility is much more important than raw performance, right? But again, some things like game design, to an extent, they are tightly coupled because why? Because you want to, you know, pick out every extra pixel and every boost in frame rate you can get. Okay. Now, so this is a good point. Any questions on any of this stuff? You've all been kind of a quiet bunch today. Anything? Everybody want to know how I got my tooth pulled yesterday? I got a tooth pulled yesterday. Got a big hole in my jaw. It hurts. It was not fun. You know, the dentist was nice. You know, the people were very nice, but you know, the experience as a whole would not repeat. Yeah. Anyway, so yeah, I had something in there that cracked, and they had to pull out the whole damn thing. They'll put an implant in later. But it's good that it's done. Anyway, I'll be eating soup and ice cream for a couple weeks, so nobody invite me to lunch. Anyway, all right, going on then. So customers, of course, are not the only users of Amazon's transaction processing system, right? There's going to be other groups involved in each transaction, right? Credit card companies for payment verification, potentially warehousing. You know, if Amazon's got to call up somebody and say, hey, we need some more of this on hand. Shipping services, outside sellers, all that sort of stuff. Amazon's got to connect with outside systems. So those systems have to interface with the transaction system to exchange notifications, right? And basically, remember we've been talking about interfaces, sending data back and forth in a standard format. One way to do that is with objects, okay? So an object is basically, if you want to think about it this way, is a list of data in a standard format. So, for example, when somebody places an order with Amazon, an invoice object will be built from the ordered items, and then possibly Amazon will wrap some metadata around it, right? Remember, metadata, data about the data, data that describes the data. So, for example, suppose you have Joe Snow. Joe Snow orders a red hat, a yellow shirt, blue pants, and a hardcover copy of Green Eggs and Ham to be delivered to 456 Igloo Circle, right? That's the invoice. So you could arrange that obviously in many different ways, but we're going to take a natural human approach to list the customer, the address, the item count, and the items. So the customer is Joe Snow, right? And if we wanted to break that down into metadata, we could say, yeah, here's the customer. It has the last name and a first name, no middle name, whatever. Here's an address, 456 Igloo Circle. And we could say that's in US format, right? So that's metadata, right? Data about the data. We could say there's the item count being 4. Again, metadata, it's the size of the list of things. Then, of course, the list of the items themselves. So you could construct it that way. Now, there are 2 main flavors to encoding this object data. The older obsolete one is called XML, which stands for Extended Markup Language. So XML, General Purpose Object Description Language, you can still find XML files out there. A lot of it is for older stuff though. But what it looks a lot like hypertext markup language that's used for web pages. So XML, the markup aspect of it basically means you have a list of text that is somehow formatted in some way. That's the marking up part. Like there's an editor making edits on it and creating structures within that. That's the markup aspect to it. Okay, it is definitely in decline, although maybe the decline has bottomed out at this point. It's still used though, but it's just, it's pretty obsolete. Any businesses trying to send a bunch of data won't do that, but you can still find like old academic stuff that uses it, or old batches of data written in XML. Anyway, the annoyances of XML, number one, it's relatively bulky. It uses a lot of extra text to code the data, which means it's going to add data. So if you have a large batch of XML data, there's going to be a whole lot more essentially text overhead. And that'll add up when you're storing data or if you're sending data over the network, right? It'll take slower to get the stuff. So this bulkiness is not good. Second, requires some kind of conversion or parsing for online use. If you want to have this object be immediately available in some sort of online application, you have to essentially write a separate program to parse that object data into whatever format you want it to be. You have to have that there. Now, that's not necessarily a huge problem, but it is an annoyance that a lot of, especially small businesses, don't want to deal with. If you are making an array, so an array is a numbered stack of the same kind of data. So imagine you have a web page and you want to display that in this invoice there are 4 items, right? And you want to associate them with links so that when the user clicks on any one of those items, it can take them to the appropriate page. Well, in a sense, to do that, you need to have this stuff linked up as an array. It works a lot easier that way. So you can say, oh, he's accessing item number 1 or number 2 or number 3 from this list, and I'll pull whatever data I need, that's stored somewhere. So if you're making arrays, which are very useful in these, these web apps, very useful for that. And last, often kind of hard to read because of the bulk of the tags. Your mileage may vary, why MMV, but most people look at this and say, yeah, this is a little harder to read than the alternative. So XML object format basically has these pointy tags. And when I say it's bulky, let's take a look at this first thing, first name, right? So the overall thing is an invoice. So there's an opening tag at the top. Down at the bottom, there's invoice preceded by a slash. That's a closing tag. Within customer, right, at the very top, customer has the attributes first name and last name. So the first name is Joe. Ahead of first name, we have this tag, opening tag, first name. After Joe, we have the closing tag, first name. Joe has 3 characters, right? First name, that tag is 11 characters. The closing tag is 12 characters. So just for that one tag, 3 characters of data, we have 23 characters of padding around that, right? It's not always that big, but I'm telling you, these tags are bulky, and if you're basically multiplying your amount of data by 3, 4, 5, 10, that's really going to add up, okay? All right. The other one, JSON. So JSON stands for JavaScript Object Notation. It's a different notation style based on JavaScript, which is code for doing active content in web pages. And towards the end of the lab, you'll do a little bit of stuff with JavaScript, and it'll be fun, I hope. Anyway, nice thing about JSON is it can be read directly by JavaScript engines and standard web browsers, right? So because JSON is already in a JavaScript compatible format, you don't need to do any translation on it. You can just take the object description the way it is, throw it right into a web app, and it'll get read correctly. Very widely used for object description these days. Now, there are some contenders out there that are trying to, push JSON out of the way. Google had one that they were working on, but it didn't really get any big traction as far as I heard. I'm sure Google still uses it internally though. But the advantages versus XML, number one, much more compact, right? Basically, you have about half as much tag data. So it reduces the amount of data storage, reduces how long it takes for data to get delivered when it's being sent over networks. And of course, no conversion or parsing needed for typical use in web apps. You don't have to have any kind of translation process, to show it on a web page. So the way JSON looks, basically like this. This is how you do what are called objects in JavaScript, and it's that same format. So JavaScript would know, oh, there's this thing called a customer. The customer has this attribute first name and an attribute last name. So in this case, we have 3 characters for Joe and 11, 12, 13. I guess that space is optional. So I'm going to say 13 characters of padding, maybe 14 if we include this front bracket. But, it's like 14 versus 23. You still need some text there to give a label to whatever thing you're talking about, but the padding is going to be a lot less than it is in XML. Because why? Because you only need the first, right? You only need the first opening tag. There is no closing tag in JSON. So you save that cost of that text. All right. And down here we see in the square brackets, see after items is square brackets. This is automatically done as an array. So if we have an array called items, instead of having to copy all of the data in the items list and store it in some kind of data structure with some translation program that we've written, JavaScript will automatically interpret this stuff in the square brackets as being an array. And it will know that this hat is the first element in the array, the shirt is the second element, and so on. And you can automatically just write code to display that for any object that has this format. So anyway, so it's more compact, it's simpler to implement in web pages. People like it. That's why it pushed XML out of the way. Okay. Questions on any of this stuff? Anything at all? Any of the stuff we have covered today? No. All right. Well, if there are no further concerns, I guess I'm going to go print out some copies for an exam this afternoon. And it's been a hoot, and thank you all for attending, and I'll see you next time.